So yeah, I'm going to show you the work I've been doing for over the last summer, where I started to play with the data from FCI. So maybe the first slide to present the capability of FCI. So if you want to see the presentation that will be better than just my single slide, you can go here. And these are the content from this presentation from Andrea Meraner, who is a guy working at UMETSAT and is in charge of developing the fire product behind UMETSAT. So quickly, there are 16 channels. 4 of them can be dedicated to fires. The 2 of them are in the infrared, and the 2 others here are in the near and visible. So mostly near infrared. So 2.2, which is quite interesting, which is at 500 meters. And then you have the 3.8, which is quite important for fire observation. So this is where you can get the FRP. That's at 1 kilometer. And then you have again another one at 1 kilometer, which is a long wave wavelength. So FCI, the data have been available since November. I think this is 24th of November, not September. And for now, we have access to the full disk data, so that every 10 minutes. And next year, we should have the same data, so same resolution, but with a time interval of 2.5 minutes over Europe. And here are some comparison between Severi and FCI. So you can see we have a much better resolution, and also a like a temperature sensitivity that is greatly improved, and that can then match the resolution, the increase of resolution. All right. So the timeline of what I've been going through since last year. So I think we started with Cyrielle to speak about the U-burn and fire monitoring in May 2024, if I got it right. And at the start, very quickly, so it was about like monitoring fires in Europe from satellite, and then came very quickly aircraft, and I was there, yes, sure, I want to do it, but I don't have any camera. So then the whole thing was a bit going nowhere, and then we managed to convince Gilles Parent from the LEMTA in Nancy to join the crazy targets to put a thermal camera above a plane in Europe, so and then in France. So and this was October 2024, and then the crazy time started May 2025. And at that stage, we didn't have, so we were going to fly a plane above fires in Europe, but we didn't have any system to monitor fire, and we didn't know how to set up the camera inside the plane. So, and all this was done within 2 months. So we managed to install the camera a week before, I think it's 2 weeks before we are starting to do the flight. And when I started working on the algorithm, so that I called FET for fire event tracking, the hotspot from FCI were not available. So when I started working on it, I worked with the VIRS hotspot, and then the hotspot from FCI were available, I think, from just a couple of days before the 15th of July. So now a slide on the capability of this algorithm. So the idea, it's nothing very new. It's just to, I've been done a lot for VIRS. I think there is a paper from, I think it's Chen et al. 2022, where they were doing it over California, so tracking a lot of fires, like large fire. And the idea was, okay, so let's try to do it for FCI so that we could get a better time resolution, and we could then have an idea of near real time of what you can do with for fire activity in Europe. So many people didn't do all this alone, of course. So that I had the help of many, especially for the implementation of the algorithm from people from IRIS that helped me a lot. So how does it work? So you start, so this is a website that we developed for the field campaign. And this is the case of the fire of Sijan. I'm going to use it a lot over the presentation, but I don't know if you see it very well, but this is your hotspot detection. So that's how the algorithm works. You receive the hotspot detection from LSA SAF. So this is the Portuguese institute that is processing the data from Meteosat to deliver in near real time the hotspot information. So we were receiving the hotspot in beta version at that stage. They were, I think, public only after the end of the campaign. So we receive the hotspot. We put a polygon above that do the convex hull around. It's actually alpha shape algorithms that do the clustering of your hotspot, and we integrate the hotspot in time. So this means that the first hotspot will stay there, and then we can build up the progression of the fire. So that's what we do here. Then you can see the plume is still going on there. And then what you can do is, like for any new polygon that do the perimeter of your fire, you can assign the value of the FRP at that time, and then you can retrieve an FRP time series that you can build up in real time. So we were having this in real time during the campaign. We could see the fire activity growing up, and then we also had the visible image at the same time. So we could track in like 30 minutes delay. This is the time you need to receive the data from Meteosat. That 20 minutes to receive the data, and then we had the 10 minutes to do the integration, and we were integrating by batch of 30 minutes. And then, so what was done is that as soon as we were receiving an information that there was some hotspot there creating a fire, we were sending a notification through a Discord group. And at the same time, we were starting through the Firecast system of Bati, we were starting a simulation on the server in Corsica, sending a request from the server that was running in Météo France. And then within, is it 1 hour after detection, we could get the direction of the plume and the propagation as well. We were not so much interested for the propagation, but this was very interesting for us because as soon as we had the detection, then we could get information of where was going to go the smoke, and then this was an important information for building up the flight plan and all the administrative things that we have to go through to have the right to fly the plane where we wanted to go. And we did this for all the fires that were in France detected by FCI. So it's a total of 475 simulations that were run on the system of Bati during the campaign. And those were like 2 examples that we had for, so this is the fires that you've been introduced by Cyril earlier this morning. So this is the one in Born, so in the middle of nowhere in Ardèche, and the one of Sijan. So those were the estimated plume height, and then this is the visible images of the propagation of the smoke. We were like, this is just an indication mostly of where was the plume spreading. For I think the plume height were relatively low, but that's because we are using a very low resolution of the model at 800 meters. So that's probably if we want to go more in details on the plume injection height, and if you are interested to link the results of 4 fires, for this we will have to increase the resolution, but that's maybe something that can be investigating at one point. But okay, so that's what we had for how the model work, and what we were doing is every hour we were outputting a report that was showing all the active fires on the area of France, and we were having the information on the FRP on the size of the. So it's not the burn area; it's the size of the polygons that are drawn above the hotspot. And then for each fire, we had a specific report where we had the time series of the FRP. This is the Corinne land cover map. That was the POFs that we were receiving from Francesca. and we were speaking about it earlier, but so this is the fire of Sijan, and here it's where the fire occurred, and that's like not so far away. You had a very high puff, so that's yeah, and those were no, but that was the puff. Sorry, for the next 2 days, and this is a puff to the day of the fire, and that's the visible images on the infrared within the last 3 hours. But yeah, so we were receiving all those information, and the whole idea was to concatenate all this to decide if we were flying or not. And this was the job of Syria. All right. Okay, so this is for what I've been doing, at least for the monitoring side on SEALEX. And then, while we were working with this, I was also in contact with Akli Ben Ali from the ISA in Lisbon. And I saw that, okay, maybe there is a way of using this algorithm to make it operational, because we were using it operationally for SEALEX, so maybe there is a way of for the firefighters also to use it. So that we, through a narrow grant, then I went just after SEALEX in Portugal to implement this onto a server that then they could be used by the ANEPS, so the civil security, civil protection in Portugal. And we did this with the help of Jorge Gomes from the VOST organization. So this is an NGO that is helping anything that is linked with risk, and especially like in Europe and in Portugal for Jorge. And again, with the help of Emmanuel Dutra from the LSA to retrieve this time we are retrieving the data from our side to, like earlier for SEALEX, LSA was sending the hotspot for us because it was a beta version. Now for this one, we are retrieving the data directly from the server. And that's, so then what we have, and this time, we were also retrieving the data from EUMETSAT to do the context. So that's the images were coming, show you it, yeah, no, so that's how it works. So the image you see at the background are in real time coming from the EUMETSAT server and processed. So that's, we were doing it, receiving the infrared 3.8, the near 2.2 as well, I don't show here, and the visible. And so within less than 30 minutes after detection, we were able to plot those and showing here, so you could retrieve, clicking on one of the polygon, you could get the time series of the FRP for each fire. And this is like a big fire that occurred 14, I think, of August, where you had the merge overnight of like 3 big fires that became a monster. The website is on. Here you have, it's not full, so you're not probably going to be able to connect, but that's this website is freely accessible. And so so then this work was published or submitted to the IFSS conference that will happen next month in June, and that's showing all the examples that we could do with this. All right. So now getting back to fire the behavior descriptor. So that's and how it started all with the conference that was organized by EUMETSAT for the release or the official release of the data from FCI. When I was there and I've seen for the first time the data from FCI, I saw that wow. But all what I've been doing before, like during my scientific career in fires, is maybe there is a way of applying directly to like the data from FCI. So this is just a slide to show what I've been doing before. So I spent a fair amount of time trying to work on the data collected during prescribed burn. And so you see that this is quite similar to what a satellite is doing. So we had an helicopter that was flying above the prescribed burns that were organized, so that burning a set of, those were stripes of plot in Kruger National Park in South Africa. And so burn was organized by the people that manage the park, and then we are just going there to fly the helicopters with monitoring the fire with 3 cameras, so that it's me here by the helicopter with there was 3 cameras inside, so a long wave, middle infrared, and a GoPro, and there was also a GoPro that was stick on the body of the aircraft. So using the data collected by from the helicopter, then we could extract the fire perimeter from the images. So I just show you here that's a time of arrival map of the different fronts that you could get, and then doing some interpolations that are like linear interpolation, but that are trying to trigger a bit the fire propagation. So I don't know if. All right. So okay. So this is it. So it's just finding a way to fill up the gap between two observations. And what I was doing is drawing all the linear propagations that you can get from any point from this like the blue perimeter to the red perimeter, going forward, backward, and then doing the interpolation of all those points within the gap inside. And then you could fill up gap smoothly between perimeter. And for the point where those like situations were not possible, this means that you couldn't draw a fixed line. Then we use a radial basis interpolation to finish the interpolation of the arrival time map. So at the end, you end up with something that is completely full. And then once you have this, you can find a way to derive your rate of spread by looking at the gradient of your arrival time map. And then if you know the direction and you know the time from the arrival time map, you can get a speed, and then you can retrieve a rate of spread map. This slide, I showed it 4 years ago, so there is nothing like in the same conference. But what I did this year is to apply the same thing to the data from FCI. So this is FCI for the fire in Aveiro in September 2014. So this is before the release of the data, so this was not like completely operational yet. There is a bit of moving of the sensor. I think they're planning to correct it. I don't know if for the data now it's still there, but that's at least back in September 2014, the data were moving a bit. So what I've been doing is, because the hotspots were not available at that time, I used a simple time series analysis for each pixel, and as soon as I have like using different thresholds, I managed to find a time of arrival for any point, like from all the point where I could apply this algorithm. And then I build up using the same strategy as I was doing for the two, like the linear interpolation between lines and then the radial basis. I can get a full map of arrival time for this fire. And what you have there in black, it's the observation where it's actually Ben Ali who did this, is like manual segmentation of data from the airborne observation from the firefighter and from FCI and from Polar Orbital Satellite. And you see that the FCI is not doing a very bad job at the end. So then, using this, I derive the rate of spread, doing the same thing that with a small scale experiment. And then you end up with, so those, forgot to mention, those data are resampled by a factor 2 to the original resolution, which is between 1 kilometer and 1 kilometer 0.5. So it's 1 kilometer in latitude and 1.5 kilometer in 1 kilometer in longitude and 1.5 in latitude for the area around Portugal. So this is sampled at half the resolution, and then like to get the arrival time map. And then from the arrival time map that is interpolated, I compute the rate of spread at it's 768 meters resolution. And then from this, the vector field, what I do is a linear interpolation of what I call fire path. So it's just like for I create a grid that is 4 times more at higher resolution than the original one. For any new point, I start a fire and I follow the path using the interpolation of the Ross vector field that I created at this resolution. And that's creating those kind of patterns. And then from this, I can retrieve a new arrival time map at 175 meter resolution, and then I can redo again the same thing to recompute a rate of spread and then reconstruct at so nearly 200 meters the fire, like the burned area. And this is what you have here. So in the background, it's your the image from FCI. In red, it's the burnt area retrieved at 200 meters, and in black, it's what Ackley did manually, doing all the input information he has. And so you don't see it so much, so very well the graph here, but that's a comparison between the two approach, and you see that the start we are not working, like it's not so good, but then when the fires start to be bigger, the algorithm works relatively well. And here it's an index showing the similarity between the different shape. Okay, and that's another example of the comparison between the two approaches, so the one from Ackley and the one I just set up with FCI. So in here you have the original, so this is the fire of Aveiro was particular because you have a very strong acceleration at 6 o'clock in the morning above a small villages that is somewhere here. And that's just the seconds of the acceleration. So it's starting at 6:05 here and ending up at 8 o'clock. And this is the data I used from FCI to build up my initial arrival time map. And then in black here, it's a density of your fire path. So you see that you have convergence in situation where you have a strong acceleration, like ellipsoidal acceleration, or merging. So you see it in more. So those are two acceleration, and here it's a merging of the front. So in red here, it's the burnt area reconstructed every 2 minutes during the propagation of the fire. And this is your associated rate of spread, and that's what Ackley could do. It's only two values of rate of spread between those two perimeters. So there is quite a lot of information. And that's the typical results that I was trying to output from those analyses. So this is here the data coming directly from the FRP from the hotspot. So this is just your time integration. And that's the probability density function of the rate of spread. So you see here, for example, that before the increase of FRP in both, you have an increase of the rate of spread. So this means that to increase your FRP, you first need to increase your fire size, and it's happening with acceleration of the rate of spread. Those are the evolution of the burnt area. So in blue here it's FCI, and here it's the information collected from the manual reconstruction of Ackley. And here in green, it's the results from the EMS, the emergency system from Copernicus. So they are mostly using the same data here, so they converge very well. FCI is slightly bigger, but then with a time resolution that is quite strong. So you can, for example, here you can see what we call the fire growth. So this is the time derivative of the burnt area, and you see that we can get much more details that what the manual reconstruction can do. And this, then it's an example of the data. So that's another website that you can't really access. But in what you see as the particle motion here is a rate of spread. So when it's red, it's a bit faster. And I put, so that's the delineation, so the fire perimeter moving. And then on this website, you can also move, like I think in the background now you have the topography, and then at one point you will switch to the visible images, I think. I'm zooming out, so that at the same time you can see the smoke. And here you have the perimeter from EFIS. So again, the match is not so bad, but it's of course the resolution is like completely different, so that we can't really expect to have exactly the same perimeter. Especially those gaps here, we completely miss them with FCI. Right. And this work was just like a preprint was published or sent to archive, and we hope to submit it very soon as well to a peer review paper. Okay, so and now the last part of the presentation. I don't know how I am with the time, but we're good. 5 minutes. Okay. So and this is another part that was of interest, and it's like main initial objective within SILEX is to try to use FCI to get data for the exercise of calibration and validation of FCI. A word on the system that we installed on board the ATR. So this is an image of the ATR 42 at the Auch airport just after the measurement we did for above the fire of Sijan. So what we had, I need here to say thanks a lot to Gilles Parent from the LEMTA, who gave us the opportunity to use 2 of his camera, but he couldn't show up at the even if he couldn't show up at the during the campaign. So many thanks. I think the cost of those 2 it's €1 million. So that was very nice of him. But so what we had is a Telops multispectral working in the middle infrared. The specs of the camera, I never dreamed about using something like this in my whole career before, but it's 8 band all in the middle infrared, a resolution of 640 by 520, and a time acquisition that can go up to 800 Hertz. So this means that you have 8 bands, each working at 100 Hertz. And then we also had a FLIR camera that is only 1 band. I mean, compared to this, it looks very bad, but it's always very cool. But 1 band, half of the resolution, and working up to 100 Hertz. So this means that we could get up to 7 bands working all at 100 Hertz. And of course, when you start working with this amount of data flow, it's not plug and play. So thanks to the help from the guy from Saphir that were very great, I think we had to build like 3 computers before getting to a configuration that could work. So this was not an easy task. And then we flew the system. So and here you don't see it so much, but this is the place where so this is serial, and then we managed to have Bati here doing the measurement. All right. So what you have, this is an overview of what's happening during the flight. So this is a middle infrared camera, and that's the long wave here. So the one of big interest is this one. We mostly here what you see is what is named the broadband. So this is from maybe I don't have it right now. I think it's 2.2 to 5.8, and it's integrated it's a large spectral response function. So this is the one that can see the background on the fire, but will be saturating during the fire. But the idea was to have a context to try to understand what we were looking at. And then this is the one I've been mostly working on now to try to work on the auto-rectification. Because when you have this data, so we are acquiring like 800 image for the 8 band one. But then you still need to auto-rectify it to try to do any processing. So the first task was to try to do the auto-rectification. So for this, we used the IMU system of the plane that work at 200 Hertz. But what I discovered relatively quickly is that the plane is not just made of one piece of metal that doesn't move. So even if we have a very good IMU, because the camera is, I think it's 4 meters behind the IMU system, then all the information you have are not exactly what the camera is doing. So then we can't really do a super accurate auto-rectification, but what I discovered is that if you calibrate, so you work on the lever arm between your IMU and your camera, and then you use this correction, and it usually, if the plane is just doing one transect, it's not so bad. So at the end, this is what we have. So this, you don't have any fire on this one, and that's the auto-rectification of the images during using the correction that was done manually on the first image, and it works relatively well. Yeah. So the plan now is to apply this strategy to all the transect, doing at every time a manual correction for the first one. And that's what I've already been working on for the fires of Sijan, and that's an example. So this is the town of Sijan the fire started here somewhere next to the I think it's a motorway, the national, I don't know exactly now. And we arrived, so this was like one of the big challenge of the SEALEX is that we had a 4 hours delay between the time we were deciding to take off and when we could arrive on the fire perimeter. So this is 4 hours. So we just arrived at this time, and what Cyrielle was showing earlier is that this fire was like stay on a plateau for almost 4 hours, then went up and then down. So we just arrived when at the end, and we could monitor the dying part of the fire. So this is at 4:47, and then the same. So another transect return at. Yeah, no, that was maybe a couple of transects in between, but that's another one at 6 o'clock. So you see the propagation of the fire in between. So each transect right now is 200 images that are stitched together. But because of I wasn't using all of them for the first exercise, so that at the end we could have up to I think it's 2,500 images on only one transect. So this means that we can get short time series information for each of the pixels here. So probably this means that we could get a rate of spread from just one transect. And that's something I will be working on if the auto-rectification is not too bad yet. So, but I think if we degrade the resolution, this could be achievable. And the resolution is about, I think, 2 to 3 meters. So we have room to degrade to try to get a rate of spread. And then that's works that I started to do a long time ago with people from CFS, and especially Joshua Johnston. It's then if you have the rate of spread and you have some information of the FRP, then you can get the fire line intensity. And this means that we might have a system that could do fire line intensity in real time, because this can work in real time. It's so the auto-rectification if you have the right data. So that's something that we will be trying to look at for the 2027 campaign. But for this, you need a stabilizer to try to get the camera as stable as possible. Okay, and then, yeah, of course, one big step coming is to the calculation of the FRP from those images. And then, for this, then we could do a comparison with the satellite, so which is the initial calibration validation. So here, for example, it's the background, it's the FRP from the FCI. Here you have the stripe from the images from the ATR-42, and here in red it's the burnt area from that was measured by Aurora Tech, so the system from Aurora Tech that were involved in the SEALEX campaign and were providing us the access to their platform to retrieve in real time the information of the whole fleet of the polar orbital satellites that they put together, and that was very helpful when we had a bit of FCI failure during the campaign. All right, so a conclusion, relatively intense 6 months, and then what come next, it's I started speaking with the Solène Turchetti and Antoine Herret from the now I forgot. They are in Jussieu in Paris, but is it Latmos? No, maybe. Okay, I think it's Latmos. Anyway, and the idea is to try to use the information I have, for example, on the, I didn't show, but what I've shown you here on the fire from Aveiro, I have the same thing for the fire of Ribot in France, and we are going to try to use it to downscale the FRP, so that if we have information of the burnt area 200 meters and 2 minutes, then we could retrieve the emission using the Happy Flam system that also use the FRP time series. And then if you have those information so that you have the dry matter emission, then you could retrieve something like the FRP that I think it will be even better than the FRP, because it will be directly your like the total energy emitted by each of your pixels. And then if you have this, you can do what I used to name with a red email from the US Forest Service that we call the burner method. This means that each single pixel acts as a burner where you have a start time of emission of your convective flux and an end time. And here, for example, it's what I developed. You don't see it so much, but it's on the ground. What you see is information from the camera, and each pixel is starting and ending with information from the camera, and the magnitude of the flux is also coming from the information from the camera. And if you put all this synchronized in time, then you can reconstruct the fire plume. This works at 2 meters with data that was at 3 Hertz. So we're going to do that for Reboot, but there is maybe a way, if we have information of heat flux at 200 meters every 2 minutes, then we could maybe do something like this for the fire of Reboot. So that's one thing that I'm quite excited to try. And then the other thing is to try to apply so the FET algorithm to the Mediterranean area. And that's, I show it here, but maybe I shouldn't, but that's very preliminary. But this is where I'm trying to go. I don't know if you see it very well, but you have the hotspot detection from FCI, so then we're clustered in time and space using FET. And I just started the things last Friday, and in 3 days, it already did 5 months. And yeah, that's why I was asking the question earlier. That's what I realized is that when if you don't pay attention too much to the filtering, then you have a lot of hotspots showing up, and that's, for example, here what you have the fire count, and this is May, I think, and you have a big increase, but this is mostly hotspots that were here in Turkey and in Algeria. So I think those are not wildfires, so I need to work more on this. But what I was trying to do for the filtering is to use the fixed hotspot from 2024 from VIRS to try to find where are the fixed hotspot, and then also the polygon from the OpenStreetMap data. But yes, I think that there is room for improvement. And then the one next thing that I want to do on this is to the forward weather spread. So the methodology that was developed for ACLI that he used on the data, he was manually segmenting the fire perimeter. I think we can do it from the polygon from the FET algorithm. So that's something that could be added here, so that we could have some statistics on the variation of the rate of spread. And then of course, it's trying to do the same thing as we are doing for SILEX, is to couple this with for fire to try to get something like injection height. So we could retrieve another fire descriptor of the fire behavior. And very excited to continue working on this. And that's it, so thanks.